All right, so we're getting to the home stretch now. Last month of the course. So what exactly are we going to be doing? Well, we're going to be covering chapters 8, 9, and 10 over the next couple of weeks, 3 weeks, I guess. And so what's going to be covered today is chapter 8. Chapter 8 is sort of a prerequisite for what we'll be covering in chapters 9 and 10. Chapter 8 is basically on what we call sampling distributions. You have a sampling distribution. What we learned about in the previous section was probability distributions. Typically, probability distributions are applied to populations. Now we're going to be dealing with samples, and we're going to be talking about different types of samples that we can have from the same population. All right, so chapter 8, the PowerPoints have 3 sections to it. Sections 1, 2, and 3, which I will cover today. All right, so section 1 talks about sampling variability. So we're going to talk about what that means, sampling variability. First thing we have to talk about also is called a statistic. You may think, well, wait a minute, I've been studying statistics, don't I? I should know what a statistic is. But in the language of what we're going to be talking about, which is called inference, which means we're going to take sample information and apply it to a larger population. A statistic is a summary number for a sample, such as the sample mean, sample median, sample standard deviation. And we use English letters to represent these. The sample mean, for example, is X, small x with a bar above it. That's a sample mean. The sample median, for whatever reason, doesn't have a symbol. We just say sample median. Sample standard deviation does have a symbol. It is the letter S. Remember, the sample variance would be S squared. So the sample standard deviation S. Then we're going to be talking about proportions today. And we're going to be using a symbol for that, which is a P with a little hat above it, representing sample proportion. Now, hold on one second. All right. Let's get back to where we were. Yeah. So hold on one second here. All right, now we're sharing. Let's go back one screen. Again, here's the definition of statistic. It is a summary value for a sample of people or things. We can calculate the sample mean, the median, standard deviation. We use these symbols. We use sample mean is X bar, sample standard deviation is S. We use proportions. We're going to use a P with a hat above it, but we'll talk about proportions a little bit later. Now, sampling variability means that if, let's say, all of you, let's say we have a population and I ask you to randomly select a sample of a certain size from the population. You're going to be measuring or something, or counting something, or asking questions, whatever it might be to those people. You're all going to get different answers for the summary statistic. All right? So for example, if all of you are going to measure the heights of everyone in your sample and then average those heights, each of you would have a separate X bar, and they all would be different from each other. All right? Because maybe you have different people in your sample. That makes sense. So the fact that the summary statistic for each sample varies from one sample to the next is called sampling variability. That's what it means. All right? It's a simple idea. Now, that complicates things a little, because then you might ask, well, is my particular summary statistic, my particular sample mean, better than other sample means in terms of being close to the population mean? Now, the population summary measure, we call a parameter. Parameter, P-A-R-A-M-E-T-E-R, parameter. So when we use a summary statistic like a sample mean, we are estimating a population parameter, such as the population mean. What? The question is, if it's normally the population parameter is unknown, if it was known, why bother doing sampling, right? We wouldn't bother with it. It's typically unknown. So the question is, how close is your sample mean to the population mean? We don't know that because the population mean is unknown, but there are certain things that we'll learn today which will help us indicate, at least indicate to us, that most likely our sample mean is close to the population mean. And how do we say most likely? We use probabilities. Probabilities determine what's most likely, right? If it's a number close to 1, right? Probabilities go from 0 to 1. If it's close to 1, that means it's highly likely. If it's close to 0, it means it's unlikely. All right, get the idea? So we're going to use probability to determine how close we are to the that our sample statistic is to the population parameter. So here's an example here. So we have a small population of 20 students, right? What are we collecting information on? The amount of money each student spends on textbooks for the semester. Right? So you ask them that question, they come up with all 20 of the students answer it. These are the 20 answers. All right. And we can calculate the population mean. Now that's a population of 20 students. So the population mean, and we use mu, the Greek letter mu, represent the population mean. We just add up their textbook expenditures, all 20 of them, and divide by 20, we get $360.25 is the average population mean. You all know how to do this. Very easy to do. Now the question is, this is a population we're aware of. What do we do in terms of the sample? Well, what are we going to do in this case here? Well, we're going to take samples of size 5. So maybe each of you will take samples of size 5 randomly from the population of 20 students. And we ask each of those 5 students their expenditures, and we average them. We add the 5 up, divide by 5, and we get an answer. All right. All right. So this is an example here of 5 of the 20 students being asked to being selected. We average those 5 numbers, $374.60. Okay. So population mean, remember, was 360.25, and this particular sample is 374.60. It's about $15 more. Is this difference typical, or is it this particular mean unusually far away? Well, the only way to know that is to do more samples, right? So more people in our class will take samples of size 5, and suppose there's 4 more of these samples here that we've done. Okay, some of them are lower, some of them are higher than the population mean. These are all means, right? So sample 2, here are the 4 students selected. We have student numbers. Each student has a number from 1 to 20. These are the students that were selected in each sample randomly. And then these are the X's that represent the expenditures for those students. So we add them up, divide by 5 for each of the additional 4 samples here. We get these sample means. Hopefully you get your understanding what I'm doing here, right? Simply randomly selecting samples of a certain size, in this case size 5, from a population of a certain size, in this case size 20. And we're choosing some samples and randomly selecting students, 5 students for each of the samples, and determining their sample means. And notice that they're all different, which would make sense if the students are different, right? All right, so the population mean we know just because of the example we're doing. And then we have these other samples. Some of them are higher, some of them are lower in terms of the sample means relative to the population. All right. Suppose we selected 45 additional random samples. Right? So here they are with their various sample means. Get the idea? So samples of size 5. We saw 5 of them. Now we have 45 additional samples with all different sample means. And so now we have 50 of them, right? 50 samples of size 5. If we used a histogram to show them, histogram would look something like this. All right. All right. And what are these? Each of the rectangles represent 20, an interval of 20. Now, what are we measuring here along the x-axis? These are individual people in the population. These are means of 5 people, sample means of 5 people. So now we're measuring sample means. How many sample means do we have? We have 50 of them because there were 50 samples. So then what are we doing here? We're creating a histogram of these sample means. All right. So many of them are going to be, so many of these sample means are going to be between 310 and 330, so many between 330 and 350, and so forth. All right. So what is the histogram? Gives us the idea of the distribution of these sample means. There's 50 samples of size 5. We're looking at the sample means. It says most samples are reasonably near 300. The population mean is 360.25. Where's 360.25? It's in this 350 to 371 here, right? So you can see most of them are fairly close, right? These 3 rectangles are the ones that are closest to 360.25. So you could see that most samples are going to be close. Now, the one that you actually get, we don't know typically if it's close or far away, but there's a good chance, as you can see just by looking at this histogram, that most of them are going to be close to the population. And that's the whole idea. The whole idea is that sampling gives us an answer, which is going to be hopefully with a high degree of probability close to the actual population. All right. Any questions about that? That was the whole idea of this particular section, just to introduce to you the idea of sampling variability. That is, if we have a population and we take samples of a certain size, in this case, they were size 5 students, and we just run samples over and over again, we're going to have a distribution of sample means, because each of those samples will have a sample mean, and then we can just list all those sample means. If we could possibly list all possible sample means, we listed all possible samples of size 5 and listed all their sample means, the distribution of those sample means is what's called a sampling distribution. It's a distribution of sample means. All right. Any questions about that? Because this is a critical concept for the rest of the course. All right. I just want to make sure. Now, many students, when they first hear this, they may be a little confused by it because you're not sure what I'm talking about or what a professor's talking about. But hopefully I did a good enough job here for you to understand that we're just repeating the sampling process over and over again. And then we're taking a summary measure, like a sample mean, for each of those samples. And then we're just listing them. And each of them will have a probability. Now, if the sampling is done randomly, then each of those samples and sample means should be equally likely to occur, right? Because each sample should be as equally likely to occur, to be chosen by you, than any other sample. It's just, luck that you got that particular sample. It's just random selection. So each simple random sampling, if we go back to that concept, means that each sample of a certain size is equally likely to occur. All right. So each of those samples has a probability associated with it, and they're equal probabilities for each of the samples. Okay. Let's now go to the second one here. This is section 2 of chapter 8. Now we're going to look at the sampling distribution, in particular of a sample mean. That's what obviously what we just did. We're going to look into a little further. All right. And this distribution of sample means, again, is we're listing all possible samples of a certain size, calculating their sample means, and then creating something like a histogram or a frequency distribution curve, something like that, to take a look at it. All right. And so that's what we're going to do in this section here. So we have a population, and whatever we're measuring, we're going to have a population mean. As I said earlier, in most cases, the population mean is unknown. That's why we're doing sampling. It's unknown, and we're not going to know it, but we're hoping to estimate it with the sample mean. Now, the sample that you get, you have a sample mean, and it'll be different than somebody else's sample mean. So the question is, how do you do the estimation if sample means vary from one sample to another? So we're going to study this a little bit in this section here, to give you an idea of how we come up with an estimate. All right. All right. Now, X bar is representing the sample mean. Mu is representing the population mean. Population also has a standard deviation, sigma. That's the symbol sigma. All right. So these are the symbols we're obviously going to be using. All right. So we're going to be doing a little experiment beginning of this section here. All right. Number one, we have a sample of a fixed size. We call it n, small n. So if there's 100 people in the sample, it's 100. It's 50 people in the sample, it's 50. That's what we mean by sample size, the number of individuals in each sample. Here, according to this, we're going to using some sort of simulation software. We're going to randomly select 500 different samples of this size, right? 500 of them. And for each of those 500, we're going to measure the sample mean. We're going to have 500 sample means. That's the whole idea. And then we're going to draw a histogram of these 500 sample means. All right? So that's the whole idea. And then one thing we could do is we're going to look at the histogram and we're going to say, all right, let's try the same experiment with different sample sizes. So maybe we'll start off with the sample size being 5. And then we'll say, all right, let's repeat the whole process with a sample size of 10 to see what the histogram looks like. 20, 30, 40. You see what I'm saying? Increase the sample size. See if that has any effect on the way that histogram of sample means looks. So that's what we're going to do. All right, so suppose we have this particular example. We're going to use this as an example. So this has to do with mean platelet volume. All right, platelets are in blood. And we're looking at a normal population mean for a measure of platelet volume of 8.3. So that's your population mean, and the standard deviation is 0.8. So what we're looking at here is a normal curve. We're assuming normal here. All right, centered at 8.3, standard deviation of 0.8. This is the population distribution, normal distribution. It's a population normal distribution. There's nothing to do with samples. All right, this is just everybody in the population, and each person in the population has a measure of the platelet volume, and that's it. All right. So we have the value of the population standard deviation 0.8 also. That shows how spread out the data that the normal distribution is. Now we're going to use some software, in this case called Minitab. We're going to select 500 random samples. We're going to start off with a sample size of 5. That means each of the 500 samples is going to have 5 people in it. Each of those 500 samples, 5 people in it. And we're going to calculate the mean platelet volume for each of those 500 samples. And when we do that and we plot it with a histogram, this is what it looks like. All right. Now, what if we increase the sample size? So that original one that we just looked at had sample size of 5. What if we repeated this whole process with 500 samples, now of size 10, 20, and 30? Now let's take a look at these again. Here's the original one. Notice that the data goes from 7.2 all the way up to 9.2 for the sample size of 5. Notice the spread of when the sample size is 10, when the sample size is 20, and the sample size is 30. Can somebody tell me a trend that you're seeing here in terms of the spread of the data and the sample size? This is a critical part of this course. So again, go ahead.
Oh, as the sample size gets bigger, the spread gets smaller?
That's it. Very, very good. As the sample size gets bigger, the spread gets smaller. Now, what is the spread in this case here? The spread is of X bar. All right, X bar. In other words, the 500 sample means. Notice that for when the sample size is 5, the spread is looks like between 7.2 and 9.2. That is the X bars, the 500 X bars. 500 sample means are between most of them are between 7.2 and 9.2. Notice when we increase the sample size to 10, notice most of them are between 7.6 and 9 or something like that. Notice when we increase the sample size to 20, notice the sample size gets even narrower. I mean, not sample size, not the sample size, the sample variability. Notice the samples are between maybe 7.8 and 8.5 or 8.7 or something like that. Notice when it gets up to 30, even a narrower spread. So the sampling distribution, that's what each of these are. The distribution of 500 sample means gets narrower as the sample size gets bigger. What else can you see by this also in terms of the shape of the distribution? Now they all look normal, but what happens to the normality? What does it look like to you? It becomes what as the sample size increases? Take a look again. Here's the original for size 5, and then 10, 20, and 30. It's not a trick question. The shape of this distribution becomes more what? What's the word I'm asking for? More blank. What word are you going to put in? More what?
Taller or thinner?
Well, thinner we already did. We talked about because that's the variability, right?
Yeah.
Thinner.
Centered.
Right? All right, be more specific. They're all centered around the same place. So be a little more specific. You're on the right track. Look at the shape here. Look at this one in particular, it's 30.
Kind of becomes like more evenly distributed.
Metric.
Right.
Like less
Say
skewed.
more symmetric, more normal, more like a perfect normal curve, right? Notice that. Now, even at 5, it looks pretty normal, but it gets more and more looking like normal as you get closer, as your sample size gets larger. That's the whole idea. Now, in this case, the distribution, if we go back to here, the distribution is assumed to be normal. The question is, what if the population distribution, remember this population distribution, if population distribution is not normal, what if it's more skewed? What happens to the sampling distribution? That's where we're going to find out in a few minutes. hopefully. All right. So each of the 4 histograms are normal in shape. Resemblance would be even more striking if each histogram had been based on more than 500 samples of size, or 500 samples. Okay. Each histogram is centered approximately at 8.3, right? If we go back, even here, 8.3 is pretty close to the center, right? Now remember, a histogram, the tallness of each rectangle indicates how many of the samples are in that interval. So you can see most of them are, many of them are in these 2 rectangles here. And that's true for all of them, right? They're all in the middle 2 or 3. So consider it to be highly likely, this is the whole idea, highly likely that if you got a sample, and if your sample size is big enough, you can be reasonably sure with a high degree of confidence that your sample has a mean that's close to the population mean. Now, it may not, but we could say with low probability, it would be far away from the population mean. With high probability, it's close to the population mean. Get the idea? That's the whole idea here. It's more likely to be close to it than it is to be far away. Okay? That's the key point here we're trying to make. All right. So the centers are approximately the same. The normality gets to be looking more normal as the sample size increases. The spread of the sample means are less as the sample size increases. But the center of it seems to be about the same. So that's 2 big things that we just learned. We learned that no matter what sample size we chose, the center is approximately near the middle. They're near the population mean, the center of the distributions are close to the population mean. And we also learned that as the sample size increases, the spread of the sample means gets narrower, gets smaller. All right. So let's see what kind of insights we can get from this. Now, if you combine these insights, it says here it yields a result that should appeal to your intuition. The X bar values, that is the sample means, based on a large sample will tend to be closer to the population mean mu than X bar values based on a small sample. All right. So that is important. All right, now we're going to get into a little bit of math, not hard math. This is not calculus or advanced math. This is algebra. So that's all you needed to know for this course is some basic algebra. Here are the symbols that we're going to use when we use our algebraic formulas. With X bar being the sample mean, small n is the sample size, mu is the population mean, sigma is the population standard deviation. Now we have 2 new symbols here, which you should get used to. Notice it says mu. We're using the Greek symbol mu with X bar in a subscript here. And what is that? That's the mean of the sampling distribution of X bar. That is, if we took the average of all possible sample means of a certain size, all right, we just took the average of all those sample means, then mu X bar would be the mean of that. All right. So in that previous example, back to this example here, if we had 500 samples of size 10, each of the 500 samples would have sample means. If we average those 500 sample means, in other words, we added up all 500 sample means and divided by 500, we would get the average of all those sample means. Right? Get the idea? Same thing over here for the when n is 20, when n is 30. So that's what we mean by mu X bar. Mu X bar is the mean of the sampling distribution of sample means. It's listed all those sample means and found the mean of them, the average of them, and we get the mu x bar. Similarly, if we found the standard deviation of all those sample means, all 500 of them, we would get sigma x bar. That's the standard deviation of the sampling distribution of x bars. It's no different than finding any mean or standard deviation. It's just, in this case, we're looking at a list of sample means. All right, those are the numbers that we're finding the mean and standard deviation of. And that's called the mean and standard deviation of the sampling distribution of sample means. Sounds like a lot of words, but that's basically what it is. Now here's something very interesting. If we could possibly list all samples of a certain size, all of them, not just 500, maybe there's 1 million of them or 1 billion of them. If we could list all of those sample means, every single one of them, all right, we found the mean of all of them. Here's algebraically what's true. The mean of all those sample means, if we had all of them, would be equal to the mean of the population. It's algebraically true. Right? There's a proof of it. We don't need to go through the proof of it, but algebraically it's equivalent. The mean of all possible sample means for a sampling distribution where the size is n, small n, whether it's size 5 or 10 or 15, 20, whatever the sample size is. We found the mean of all those sample means, the mu x bar, is going to be equal to the population mean, period. Another property is this, and this formula here explains why, as the sample size goes up, the distribution of sample means becomes more narrow, which means the standard deviation of the sample means gets smaller. This formula says if we take the population standard deviation and divide it by the square root of the sample size, you get the standard deviation of the sampling distribution of sample means. And notice that the numerator is fixed. It's a fixed number. It's the population standard deviation. It doesn't change. It's absolutely fixed. The denominator, however, has the square root of the sample size. Okay. And hold on one second. No, you should order it. All right. All right. Now, let's say this once again. The sampling distribution of sample means we took the standard deviation of all those sample means. It would be equal to the population standard deviation divided by the square root of the sample size. This fraction here, notice the numerator is fixed and the denominator is based on the sample size. Notice as n, the sample size increases, the denominator, even though we take the square root, the denominator will get bigger. The numerator is still fixed. Whenever we have a fraction, we learned this in arithmetic, whenever we have a fraction and the numerator is fixed and the denominator is getting bigger, the fraction gets smaller, right? It's true. Like the fraction 1/2, if we increase the denominator from 2 to 4, the fraction becomes 1/4, and 1/4 is smaller than 1/2. So that is the rule, and we see it actually using a computer simulation for it to be true. The larger the sample size, the smaller the spread of the sampling distribution, and the smaller and then the spread is being measured by the standard deviation of the sampling distribution of sample means. Now it says here a little footnote. It says this formula is exact if the population is infinite. Most populations aren't necessarily infinite. And is approximate correct if the population is finite. And here's another important piece of information, that the sample size is no more than 10% of the population size. And the sample size has to be less than or equal to 10% of the size of the population for this formula to work pretty well, all right, for it to be a very, very good approximation to the actual population standard deviation, to the actual standard deviation of the sampling distribution. All right, but we use it anyway. We're always going to assume this. Whenever examples I give you, we're going to assume that the sample size is less than 10% of the population size. All right, and that's most in those real situations. That's typically true. All right, so these are the two formulas we're going to be using. This is what you need to know. These two very simple formulas. That the sampling distribution has a mean that's equal to the population mean, and that the sampling distribution has a standard deviation that's equal to the population standard deviation divided by the square root of sample size. These are the two things that you need to know. Property 3, when the population distribution is normal, this is very important, the sampling distribution of sample means is also normal for any sample size. So we could have, and we noticed that in that previous example. This example here, let's go back to it. Here's the population distribution. It's normal. So it didn't matter what sample size we had. Even with sample size 5, it looks pretty normal. Okay, all of them look normal, except they looks more normal as the sample size increases. But even for a small sample size, the histogram looks normal. That's because the population is normal. All right. However, if the population is not normal, maybe skewed left, skewed right, then we have something called the central limit theorem. This is a main theorem in statistics. What this theorem basically says, without getting into any math regarding it, it says when the sample size is sufficiently large, then the sampling distribution of sample means is well approximated by a normal curve. In other words, we can assume a normal curve, even when the population distribution is not normal. Now, why is this important? The reason this is important is because if we can use a normal curve, guess what? We can use our calculator, normal CDF with our calculator, inverse normal, all those features of our calculator to come up with what? Come up with probabilities. We can calculate probabilities, things like that. So that's why the central limit theorem is so important. Because what we're really interested in when we're doing inference is we don't know anything about the population, but we do know something about our sample. And our sample has a sample size. All right, it has a sample size. And that's important because then we want to make sure the sample size is sufficiently large enough so that we can assume that that sampling distribution is going to be approximately normal. And then we can use our calculator to calculate probabilities. That's why we want to do this. And that's why the central limit theorem is so important. Without the central limit theorem, our course would end today. We wouldn't have anything else to say. And you could just, I would just distribute the grades and the course would be over. But unfortunately for you, the course is not over. You have to go through this process. But once you learn how to use these tools with your calculator, it's not so bad. All right. But the central limit theorem is the reason why we can use these tools. All right. Now, it says here, it's just going into a little more detail about these properties. The property number 1 is very important because we can always, if we're given, if we know the mean of the sampling distribution, that's the population. They're equal to each other. That's number 1. So the sampling distribution is always going to be centered at the mean of the population. So if we have that normal curve for the sampling distribution, the middle of it is going to be the mean of the sampling distribution, but it's also the population. We're assuming the population mean is right in the center of the normal curve. Notice here that the sampling, the standard deviation for that normal curve is going to be sigma x bar. All right, because what is the normal curve of? It's the normal curve of the sampling means. The sampling means have a distribution that's normal, brought from the normal, and this is the standard deviation. It's the population standard deviation divided by the square root of n. So again, even if the population is not normal, if n is sufficiently large, we'll talk about what that means in a minute, then we can use this formula for the sampling distribution standard deviation. Okay? And we notice again, as n increases, this sigma x bar decreases. Okay? Very important part of this course is understanding that basic property. So for example, if the sample mean is 4, the square root of 4 is 2. That means that the sampling distribution has a standard deviation that's 1/2 of the standard deviation of the population. Remember, it's the square root of that here. So if the sample sizes goes up, sample size is 4, all right, then it's standard deviation, then the standard deviation of the sample distribution is 1/2 of the population standard deviation. All right. That's true for any value of n. If n is 16, square root of 16 is 4. That means if the sample size is 16, the standard deviation of the sampling distribution is 1/4 the size of the population standard deviation, because the square root of 16 is 4. All right, you get the idea how this works? Again, when we get to tests, questions on tests and final exam especially, I like to ask questions like that. Final exam questions. My final exam questions would be something about this property right here. Notice what the normal curves look like for a for sampling distribution as the sample size gets bigger. Now, they're drawing here the population. Notice the population distribution is also drawn on this graph. So that's that. And notice that for n is 4, that is the this one right here. So it's less spread out, right? The spread, an average spread is 1/2 of the spread of the population. So this is the spread of the population, and this is the spread of the sampling distribution when n is 4. And look when n is 16. Here's the spread of the sampling distribution when n is 16. It's 1/4 of the spread of the population, the average spread. All right, so you get the idea here? So here's the deal. When n is large enough, most of the values of most of the sampling means that could possibly exist are going to be very close to the true population mean. That means that the larger the sample size is, the better estimate the better estimate is your sample mean. The better estimate of the population mean is the sample mean that you actually got. There's a very high probability that that sample mean that you have is going to be pretty close to the population mean. It's a good estimate, most likely. So the larger the sample mean, the sample size, the better that estimate is. That's why we want, if possible, bigger sample sizes. Now, notice in this chart here, notice that the population is skewed to the right. It's not normal. Now, notice what n is 4. Here's that curve here. The spread is less, but it's still skewed. But then when n gets to 16, hey, it looks pretty normal, the sampling distribution. All right, so even when the population distribution is skewed, eventually, with a sufficiently large n, the distribution of sample means, all right, the sampling distribution starts to look normal. And then we can use the normal features of your calculator, all right, to make calculation, all right? All right, so that's, now, here's a little formula here. Now, we know what a z-score is, a standard score. Remember back when we looked at those, z is equal to remember, let's say we had a test, and the test has a population mean and a standard deviation. We wanted to calculate the z-score for your particular test score. We took your test score and subtracted the mean and then divided by the standard deviation, and we ended up with our z-score. And our z-score told us how many standard deviations above or below our score was from the mean. We could do the same thing with the sampling distribution. We can calculate the z-score for a sample mean instead of for an individual. So for example, again, with the test scores, if we had a sample of size 10, so we sampled 10 people and determined their scores on the test, we could then calculate the average for those 10 scores, the average score for those 10 people, and that would be our sample mean score. And then that would be our X bar in our standard score formula here. So we, instead of having X here, which would be one person's individual score, here we have a sample mean. In this case, I was saying 10 people's average score. We would subtract from it the population mean, or in this case, the mean of the sampling distribution, which is the population mean. And notice what we divide by, the standard deviation, but it's not the standard deviation of the population, it's the standard deviation of the sampling distribution. So now when we calculate our standard score or z-score, we want to know how many standard deviations the average is from the true population average. We're going to use this formula now, because now we're dealing with sample means, not individual scores, but means of scores. All right? And so we need to subtract from the sample mean the mean of the sampling distribution and divide it by the standard deviation of the sampling distribution. Now, in this next part of the formula, we know that the mean of the sampling distribution is equal to the population mean, and we know that the standard deviation of the sampling distribution is equal to the population standard deviation divided by the square root of the sample size. So that's where this formula comes in here. And if you know the mean of a population, and if you know the standard deviation of the population, and if you know the sample size, you can now calculate the z-score. And it tells us how many standard deviations away the sample mean that we're looking at is from the true population mean. That's what it's really telling us. Any questions about that? Now, we mentioned earlier that our samples, if the population distribution is skewed, not normal, or unknown, we want to know how large should our sample size be before we make the assumption that the sampling distribution is approximately normal. And most people have come up with this rule of thumb, and it's greater than or equal to 30. So if the sample size is at least 30, we can make that assumption. If the population distribution is unknown or if it's skewed. Now, if we know that the population distribution is normal, then the central limit theorem doesn't apply, and it could be any size, and we can assume the sampling distribution is normal. So here's an example here. It says a soft drink bottler claims that on average, and they're making this claim, so what are they claiming? Something about the population. They're assuming here that on average, cans contain 12 ounces of soda. All right, so that's a population assumption here. Mu is equal to 12. They're also saying that this is normally distributed. We had all the cans of soda that ever existed. We would assume that the distribution of the ounces are normal, and the mean is 12 ounces because the can is saying 12 ounces, and the standard deviation is 0.16 ounces. All right, so there's not much variability between different cans of soda. Suppose you pick 16 cans at random from an assembly line, let's say, and then you're going to measure the soda volume for each of those 16 cans. Let's say you repeat this process over and over again, and you get I'm sorry, then for each of these cans, you would calculate what? For each of these samples, you would calculate the average volume. You have 16 cans. You measure the volume of soda in each one of those cans, and then you find the average of those 16 volumes. And that's X bar. Okay. So sample size is 16. That's N. Population mean is 12. Population standard deviation is 0.16. All right, that's all we need to know. And let's go to the next page here. Let's say we wanted to calculate the standard deviation of the sampling distribution. What would that be? It would be the population standard deviation divided by the square root of the sample size. 0.16 divided by the square root of 16 is 0.04. Make sure you do this with your calculator so you don't make any mistakes. What is the mean of the sampling distribution? It's equal to the population mean. We mentioned that earlier. That was one of the properties. So it's 12. So our sampling distribution will be centered at 12, just like the population is. But we'll have a standard deviation smaller than the population standard deviation by 1/4, right? It's 1/4 of the size of 0.16, it's 0.04. Now we can calculate the probability, all right? We can calculate probabilities. Now it says here we need to standardize. But with our calculators, remember that our calculators can calculate probabilities using X or X bar without converting those values to Z's, right? We don't have to do that. Our calculators does that for us. We just use normal CDF to answer the question. So we don't have to follow that step there. We don't have to convert it to Z's. I mean, you should be familiar with how to do it, because I could ask you a question how to do that. But certainly, you don't have to do that to calculate the probabilities. So for example, if you wanted to know what is the probability that a sample of size 16 has a mean between 11.96 ounces and 12.08 ounces. Now let's think about what we're asking here. We're saying we have a size of 16 cans. We want to know what's the probability that the average volume of those 16 cans. So we add up all their volumes and divide by 16. It's the probability that that average is between 11.96 ounces and 12.08 ounces. Okay. I'm actually going to write this down. I'm going to use our calculator to show you how easy it is to do this. Now remember, let's go back one. They calculated the standard deviation of the sampling distribution. Now we know the population standard deviation is 0.16, and we know that the mean of the population is 12. We want to calculate what's the probability that our sample mean of 16 cans is it's going to be somewhere between 11.96 and 12.08. So this curve here is not going to be the population curve. It's going to be the curve of the sampling distribution of sample means for size 16, sample size 16. These represent sample means, all possible sample means for 16 cans of soda. So that's what we're interested in. So this distribution here is not the population curve. It is the sampling distribution curve. So let's go to the calculator. Now, once again, to get to our normal CDF, we're going to go to second, the ARS. And we're going to scroll down the normal CDF. Now, this is the way I would recommend doing this type of problem. Now remember, lower and upper represent the interval, right, for the normal curve. The lower interval, the upper part of the interval. And we're given that information. The lower is 11.96. And the upper is 12.08. 12.08. Oh, I keep doing that. I guess I better use this here. 12.08. Now, the mean, now remember, the normal curve here is the sampling distribution. It's mu x bar. We know mu x bar is equal to mu, which is 12. Type in 12 here for the mean. The standard deviation is the standard deviation of the sampling distribution. Well, this is the way I would do it. I wouldn't waste my time calculating what the standard deviation of the sampling distribution is exactly. Why don't you just put the formula in? I'm going to put, now remember the standard deviation is, for this problem, what was it again? It's 0.16. So for the population, so it's 0.16, and then you could just put a formula in here, divide by the square root, that's second, there's the square root, simple. And how many cans are there? There's 16. Close parentheses. So look what I put in here. I put in the formula for the standard deviation of the sampling distribution. Put it directly in here. Why bother calculating when you just put it in here and then the calculator calculates it for you? So this way you don't make any errors. All right, you don't make any math errors. You just type in the formula for the standard deviation of the sampling distribution. Scroll down, hit enter. Those of you with the 83 calculator, again, this is the order in which you put things in. Lower, upper, mean, and the standard deviation of the sampling distribution. Hit enter again. There's your probability. There's your answer. 0.8186 if you're rounding the 4 decimal places. Any questions about that? So when you're dealing with samples, sample means, this is how you find the probabilities. All right. Okay. Now, here they converted both the lower limits and the upper limits to z's. Waste of time. Don't need to do that because your calculator does this for you. It converts everything you put in there to z's. So don't bother with this unless you're being specifically asked what is the z for the lower limit or the z for the upper limit. I wouldn't bother with it. All right. And notice here they found the area using z's after they converted from x bars to z's. No need to do that. Your calculator does it for you. Any questions? And I have no idea why these books continue to show this. They're assuming, I guess, that maybe people don't have TI-83, 84 calculators, but I think most people do when they take these courses. All right. Any questions about that? Now, if n is too small, then, for example, less than 30, and the distribution, the normal, then the distribution of the population is either unknown or skewed, not normal. Then if n is less than 30, we can't use these formulas. These formulas won't work. The central limit theorem has to be used. And again, n has to be at least 30 if the population distribution is not normal or unknown. So unfortunately, these formulas don't work very well in that case. All right, so let's now get to the last section. We have about 15 minutes, I think. Last section, we can easily do this. We're going to be talking about a statistic called a sample proportion. So this is not a mean. These are proportions. We have to talk about what a proportion is first. Many times we're interested in statistical studies, the proportion of people, or percentage of people, who might be interested in a certain topic, or who may be interested in voting for candidate A versus candidate B, something like that, right? So we're basically counting the number of people in these categories, and then we find the proportion of those people that we counted. So if we have a survey of 1,000 people, and 600 people like candidate A, then 600 divided by 1,000, or 0.6, is our sample proportion. It's the proportion of people who like candidate A. That's what we're talking about. All right. So we're going to use different symbols with proportions than we are with means. But the whole idea is the same thing with sampling distribution. Right? We want, of course, we want to estimate, we want to take our sample proportion, estimate the population proportion. For example, when that political poll is done, we want to see how well that political poll is, its estimate to the true population proportion. How many people really like candidate A as opposed to people who are in our poll. All right. So this is a binomial type situation typically. We have two choices, either candidate A or the other candidate, or the other candidates. That maybe that's the other choices, all the other candidates. And we consider the choice that we're interested in, we call that a success when we see it, when we count it, and the other choices are considered a failure. So they use this term success versus failure, but success just means one of those two choices that we're interested in, and the other one is a failure. All right. So if we flip a coin and we're interested in counting the number of heads, then heads is success and tails is a failure. All right. If we're interested in counting the number of tails, then tails is a success and heads is a failure. So it's just the one that we're interested in. That's what it means. So when we say proportion of successes, if we flip the coin 100 times and we want to count the number of heads, it's the number of heads divided by 100 gives us the proportion. Now for the population proportion, the true population proportion, we're going to use P. And the sample proportion, we're going to have P with a little bit of a hat above it. All right, upside down V, that's what the hat looks like. So P itself represents the proportion of successes in the population. P is always going to be between 0 and 1 because it's a proportion, right? It's always going to be that way. Has to be, right? If you have 100 people polled and you want to know how many people are interested in candidate A, it's either going to be 0 up to 100. So it can't be more than 100 if there's 100 people being polled. So the proportion is always between 0 and 1. If P is 0.75, that means 75% of the population like candidate A, right? Something like that. P is 0.01, that means only 1% of the population likes candidate A. So hopefully that makes sense to you. And then if we took a sample from the population, then we could count the number of successes in that sample and divide by the number of people in the sample, small n. That's P hat. That's a sample proportion of success. So that's the symbols that we're going to use. All right, so here's an example here. We'll just run through the example, a couple of examples, and then we'll be done. This section, chapter 8. It says development of viral hepatitis after a blood transfusion can cause serious complications for patients. So there are 300, there's a sample done of 342 blood donors, ages 18 to 45. And it says here, out of the 342 in the sample, 7% tested positive for this virus. So this is viral hepatitis, 7%. So 7% or 0.07 is the sample proportion. Now, if you wanted to know the exact number of people in the sample who had tested positive for this, you would just obviously multiply 342 times 0.07, and that would give us the sample, the number in the sample who tested positive. All right. Now you can do simulations of this also, right? Simulations where you took different samples of different sizes. So let's see. Now, in this particular case here, this is a little confusing because they use the word sample here. They're considering the 342 to be a population, all right? Just for illustration purposes, that's what they're doing. So they're considering P to be equal to 0.07, not P hat. And then they're saying, we're going to use P is equal to 0.07 as our population proportion. And let's do some simulations using samples of different sizes. So from that population of size 342, we're going to take samples, 500 samples of size 10, 25, 50, and 100, and look at the distribution of the sample proportions. All right. So each of those samples will have a sample proportion, and then we're going to look at the histograms for each of these 4 curves. This is what they look like. Notice that when n is 10, when the sample size is 10, so that means we have 500 samples of size 10, distribution of sample proportions is skewed to the right. We increase the sample size to 25, still skewed, but not as skewed. And now as we increase the sample size to 50, it looks better. And certainly at 100, it looks pretty normal. So obviously here, as the sample size increases, the sampling distribution starts to look more and more normal. It looks like something similar to what we're seeing with sample means. All right. Now, it says all 4 histograms are centered approximately near the sample proportion of 0.07, right, which is right around here. 0.07 would be in this first bar because it's centered at 0. All right, so somewhere in this first bar is 0.07. Over here, somewhere in here is 0.07 in the middle. Now, when I say middle, I mean somewhere here. I shouldn't use the word middle. I should say towards the left here is the 0.07, 0.07, 0.07. You can see that the center, now here it's more in the middle, right? Because this is more normally more like a normal curve, but it's in the middle here. So all the curves are have a mean approximately close to that mean of 0.07, which is the population proportion. Okay, so one of the things that we just discovered, and what just happened here? Whoop, here we go. Sorry about that. All right. Now, let's look at the properties of p hat. The distribution of all these p hats, 500 of them that we were just looking at. All right. Again, the symbols that we're going to use, fewer symbols actually in this case, and with the sampling distribution of means. Here we're going to use sampling distribution of sample proportions. P hat is the sample proportion, n is the sample size, p is the population proportion. Now, if we were able to list all samples of size, whatever the sample size was, 50, 100, whatever it might be, and average all those sample proportions, if we were able to list all of them, come up with this property number 1, that the mean of all those sample proportions is equal to what? The actual population proportion. All right? Those two are all equivalent to each other. They're equal to each other. The standard deviation of all those sample proportions, here's the formula. It's the square root of what? P, which is the population proportion, times 1 minus p divided by n. The square root of that fraction. N is the sample size. All right. So here are the mean and standard deviation that would determine what? The normal curve, right? The normal curve. Now, property, now, again, this formula is exact. The population is infinite, normally isn't. And again, approximately correct, that standard deviation formula if the population is finite and no more than 10% of the population is included in the sample. Same thing as we saw before. Now, property 3 says when the sample size is large and the p, all right, the proportion is not too close to 0 or 1, the sampling distribution of p hat is approximately normal. Okay. So notice that the p hat, the sampling distribution of p hat is centered right where the population proportion is, which is a good thing. We want that. And we notice that if we go back, that is as now p and then 1 minus p fixed. The denominator is n, sample size. Notice as n increases, this whole fraction decreases and the square root of it decreases. So once again, the standard deviation of the sampling distribution decreases as the sample size increases. Same thing as we saw before. All right, now what's different about this is the idea for proportion. The further the value of p is from 0.5, the larger n must be in order for the sampling distribution to be approximately normal. Fortunately, we have this formula. This is what you need to know. Again, you don't need to memorize it. This is something that you have available. What we do is to find whether a sampling distribution of sample proportions is normal, approximately normal, you need to do these two little calculations. We take n, the sample size, and multiply it by p, and then we take n and multiply it by 1 minus p. If both of these calculations are at least 10, then we can say that the sampling distribution is approximately normal. And that's how we determine it. Population is never going to be normal, by the way, because it's binomial. All right? It's not going to look normal. But definitely, for us to use a normal distribution, this is the calculations we do to make that determination. And this is something you need to know for the final exam. It's going to be asked. I can assure you, you're going to have to do that little bit of a calculation. All right? And then they do, more examples here of it. And oops, sorry about that. I don't know why my computer is doing this. It's weird. We only have a minute left here. I want to show you this example here. So we want to calculate. Suppose we had, let's see what it says here. All right, so we're assuming the population proportion is 0.07. Suppose we took a sample of size 200, and suppose out of those 200, only 6 of them contracted hepatitis, and those tested positive. So 6 divided by 200 is our sample proportion. Okay, and if you calculate, it's 0.03. So it says the question of interest is, does this result indicate that the actual proportion of donors who test positive with hepatitis C when the new screening procedure is used is less than 0.07, blah, blah, blah. All right. Well, to calculate, if we assume that the population proportion is 0.07, the sampling distribution is going to also be 0.07. And we can calculate the standard deviation of the sampling distribution by plugging in 0.07 in here. We know our sample size is 200. So 0.07 is the mean of the sampling distribution, and this square root here is the standard deviation of the sampling distribution. Now, once again, when we use our normal CDF on our calculator, we just plug in this square root into that, plug in that formula for the standard deviation. And that's what we do. All right. We do this calculation to make sure that these numbers are greater than 10. That means we can use the normal. And if we want to know what's the probability that p hat is less than or equal to 0.03, and we choose a sample size 200, what's the probability that we get 3 or fewer, we get the sample proportion is 0.03 or less? Okay. So how do we do that? We go to our, I know we're running a little late, but let's just do the calculation really quickly, show you how it works. Again, we do normal CDF. Now, if it's less, if the probability is less than, we use negative 1,000 for the lower. What we're going to do. And we'll use 0.03 for the upper. That's the proportion, 0.03. The mean is 0.07. Remember that. And now look what I'm going to do for the standard deviation. I'm going to just put in the whole formula. I'll do square root. And I'm going to put 0.07 here times, I'll put an open parentheses, 1 minus 0.07, 1 minus 0.07, close parentheses. Okay. Then I need another set of parentheses to close out the square root. No, excuse me, I'm sorry. Then I do divide by 200, so sample size. And now I close out the square root. So the numerator is 0.07 times 1 minus 0.07. Denominator is 200. It's all inside that square root. I scroll down, hit enter. That's what I would put in if I was doing the TI-83. There's my answer. Probability is 0.01. It's a very small chance, 1.33% chance that I would get a sample proportion that small. All right. So that's it. That's all we'll do today. Any questions? It looks like I wasn't sharing the screen with you with that, so I apologize. Let me just share that screen. Let's show you what I just did. Hold on. Nobody said anything, so this is I'll do it very quickly again. So I know I'm running a little bit over, but I'll show you what I set up inside the normal CDF for this. And there it is. That's how I set it up. -1,000, 0.03 for the upper. That's the probability that he had is less than 0.03. Here's my mean of 0.07. Here's my standard deviation of the sampling distribution. And then I just hit enter and I get my answers, 0.013. All right, so that is it for today. That is chapter 8, by the way. You should read through chapter 8. It's very important to read it. Just don't depend on the videos or the PowerPoint slides. You need to read it to do better on it. All right, and I will give some homework, but not yet, because I want to also start chapter 9 next time. All right, and we'll talk about homework next time. All right, so that's it. I'll stop the recording.